Classification of database management system. Classification based on data model. The most popular data model in use today is the relational data model. Well-known DBMSs like Oracle, MS SQL Server, DB2, and MySQL support this model. Other traditional models such as hierarchical data models and network data models are still used in industry, mainly on mainframe platforms. However, they are not commonly used due to their complexity. These are all referred to as traditional models because they preceded the relational model. In recent years, the newer object-oriented data models were introduced. This model is a database management system in which information is represented in the form of objects as used in object-oriented programming. Object-oriented databases are different from relational databases, which are table-oriented. Object-oriented database management systems, or OODBMS, combine database capabilities with object-oriented programming language capabilities. The object-oriented models have not caught on as expected, so are not in widespread use. Some examples of object-oriented DBMSs are O2, Object Store, and Jasmine. And now for classification based on user numbers. A DBMS can be classification based on the number of users it supports. It can be a single user database system which supports one user at a time, or a multi-user database system which supports multiple users concurrently. And then classification based on database distribution. There are four main distribution systems for database systems, and these in turn can be used to classify the DBMS. First is the centralized systems. With a centralized database system, the DBMS and the database are stored at a single site that is used by several other systems too. And then you have your distributed database system. In a distributed database system, the actual database and the DBMS software are distributed from various sites that are connected by a computer network. Third are your homogeneous distributed database systems. Homogeneous distributed database systems use the same DBMS software from multiple sites. Data exchange between these various sites can be handled easily. For example, library information systems by the same vendor, such as GIAC Computer Corporation, use the same DBMS software, which allows easy data storage between the various GIAC library sites. And fourth are your heterogeneous distributed database systems. In a heterogeneous distributed database system, different sites might use different DBMS software, but there is additional common software to support data exchange between these sites. For example, the various library database systems use the same machine-readable cataloging, or MARC, format to support library record data exchange. Now let's talk about support for fast lookup. Most database software includes indexing technology that enables sublinear time lookup to improve performance, as linear search is inefficient for large databases. Suppose a database contains n data items, and one must be retrieved based on the value of one of the fields. A simple implementation retrieves and examines each item according to the test. If there is only one matching item, this can stop when it finds that single item. But if there are multiple matches, it must test everything. This means that the number of operations in the worst case is O(n), or linear time. Since databases may contain many objects, and since lookup is a common operation, it is often desirable to improve performance. An index is any data structure that improves the performance of lookup. There are many different data structures used for this purpose. There are complex design trade-offs involving lookup performance, index size, and index update performance. Many index designs exhibit logarithmic O log n lookup performance, and in some applications, it is possible to achieve flat O1 performance. Now let's talk about policing the database constraints. Indexes are used to police database constraints such as unique, exclusion, primary key, and foreign key. An index may be declared as unique, which creates an implicit constraint on the underlying table. Database systems usually implicitly create an index on a set of columns declared primary key, and some are capable of using an already existing index to police this constraint. Many database systems require that both referencing and referenced sets of columns in a foreign key constraint are indexed, thus improving performance of inserts, updates, and deletes to the tables participating in the constraint. Some database systems support an exclusion constraint that ensures that for a newly inserted or updated record, a certain predicate holds for no other record. This can be used to implement a unique constraint with equality predicate, or more complex constraints, like ensuring that no overlapping time ranges or no intersecting geometry objects would be stored in the table. An index supporting fast searching for records satisfying the predicate is required to police such a constraint. Now let's talk about index architecture or indexing methods. First, non-clustered. The data is present in arbitrary order, but the logical ordering is specified by the index. The data rows may be spread throughout the table regardless of the value of the indexed column or expression. The non-clustered index tree contains the index keys in sorted order, with the leaf level of the index containing the pointer to the record, or page and the row number in the data page in page organized engines, row offset in file organized engines. In a non-clustered index, the physical order of the rows is not the same as the index order. The indexed columns are typically non-primary key columns used in join, where, and order by clauses. There can be more than one non-clustered index on a database table. Clustering alters the data block into a certain distinct order to match the index, resulting in the row data being stored in order. Therefore, only one clustered index can be created on a given database table. Clustered indices can greatly increase overall speed of retrieval, but usually only where the data is accessed sequentially in the same or reverse order of the clustered index, or when a range of items is selected. Since the physical records are in this sort order on disk, the next row item in the sequence is immediately before or after the last one, and so fewer data block reads are required. The primary feature of a clustered index is therefore the ordering of the physical data rows in accordance with the index blocks that point to them. Some databases separate the data and index blocks into separate files. Others put two completely different data blocks within the same physical files. When multiple databases and multiple tables are joined, it's referred to as a cluster, not to be confused with clustered index described before this. The records for the tables sharing the value of a cluster key shall be stored together in the same or nearby data blocks. This may improve the joins of these tables on the cluster key, since the matching records are stored together and less I/O is required to locate them. The cluster configuration defines the data layout in the tables that are parts of the cluster. A cluster can be keyed with a B-tree index or a hash table. The data block where the table record is stored is defined by the value of the cluster key. We know that data is stored in the form of records. Every record has a key field, which helps it to be recognized uniquely. Indexing is a data structure technique to efficiently retrieve records from the database files based on some attributes on which the indexing has been done. Indexing in database systems is similar to what we see in books. Indexing is defined based on its indexing attributes. Indexing can be of the following types. Primary index. Primary index is defined on an ordered data file. The data file is ordered on a key field. The key field is generally the primary key of the relation. Secondary index. Secondary index may be generated from a field which is a candidate key and has a unique value in every record, or a non-key with duplicate values. Clustering index. Clustering index is defined on an ordered data file. The data file is ordered on a non-key field. Ordered indexing is of two types: dense index and sparse index. In dense index, there is an index record for every search key value in the database. This makes searching faster but requires more space to store index records itself. Index records contain search key value and a pointer to the actual record on the disk. In sparse index, index records are not created for every search key. An index record here contains a search key and an actual pointer to the data on the disk. To search a record, we first proceed by index record and reach at the actual location of the data. If the data we are looking for is not where we directly reach by following the index, then the system starts sequential search until the desired data is found. Now let's talk about multi-level index. Index records comprise search key values and data pointers. Multi-level index is stored on the disk along with the actual database files. As the size of the database grows, so does the size of the indices. There is an immense need to keep the index records in the main memory so as to speed up the search operations. If single-level index is used, then a large size index cannot be kept in memory, which leads to multiple disk accesses. Multi-level index helps in breaking down the index into several smaller indices in order to make the outermost level so small that it can be saved in a single disk block, which can easily be accommodated anywhere in the main memory.